Greetings, this is Greg. The Martin B-26 Marauder had decent performance and a solid war record, but it's been overshadowed by nearly every other frontline U.S. bomber. The U.S. heavy bombers get a lot more recognition. So does the B-25 Mitchell. Like the Marauder, the Mitchell is a medium bomber, but gained a lot of fame from the Doolittle raid and its other exploits in the Pacific. The Marauder has some impressive exploits as well, but the timing was always such that they were overshadowed by other things going on during the war. Let's take a look at the plane itself. Of all the planes in World War II, and especially among the U.S. airplanes, the Martin B-26 has the most confusing combination of variants. So for purposes of this video, I'm going to break them up into what I'll call early and late models. The early models are the ones with the shorter 65-foot wingspan and slightly less powerful versions of the Pratt & Whitney R2800 engines. The later models had the wingspans increased to 71 feet, a taller tail, slightly more powerful versions of the R2800s, and various other changes. I can't cover everything about this plane in one video, so I want to talk about three main topics: the plane's speed, its bad reputation as an unsafe airplane, and its abnormally high cost. I'm going to focus on the early models with the 65-foot wingspan. The Marauder suffered real damage to its reputation during the war, partially because it was a very dangerous airplane to train in and because it was a point of focus for the Truman Committee. That committee was tasked with looking into war production waste, inefficiency, and war profiteering. Now, I've had quite a few people on Patreon ask me, why was the B-26 so slow? The Marauder has Pratt & Whitney R2800s, which are powerful. It certainly looks sleek, and yet its top speed is usually only listed at 287 miles per hour. There are a few factors at work here, not the least of which is the plane's size. The B-26 is a big airplane. I think people tend to compare its speed to much smaller airplanes like the Bristol Beaufighter or the A-20 Havoc, maybe even the Mosquito or A-26 Invader. Those airplanes are all attack aircraft and are not in the same size range as the B-26. Just looking at a Marauder, it doesn't look that big. For some reason, it's deceptive. The plane is probably bigger than you think. This doesn't really come through in pictures. Even if we compare the early, smaller A-model Marauder, it's bigger in most dimensions than a B-25 Mitchell, and generally has a higher maximum takeoff weight, although that depends a little bit on which variants you're comparing. If we compare an early 1942 B-26, like an A model that we're using here, to a 1944 B-25J, they both normally max out around 36,000 pounds. But apples to apples, the Marauder is usually the heavier of the two. The Marauder is also much larger than the German Ju-88 and larger in most dimensions than a Heinkel HE-111, although the German planes, especially the Heinkel, have a greater wingspan and quite a bit more wing area. Compared with the Heinkel, though, the B-26 is longer, taller, and has a maximum weight around 3 tons higher. This chart shows various airplanes that are comparable to the Marauder, and as you can see, the B-26 has a very high maximum takeoff weight for a twin-engine medium bomber. Its overall dimensions are big, although its wingspan is on the shorter end of the scale, and while it's not shown on this chart, its wing loading is much higher than the others. I'll get to the speeds in a moment, but for now, just know that the Marauder is the fastest plane on this list. The Marauder only seems slow, well, one of the reasons it seems slow is because we tend to compare its speed to planes that are really in different categories. Another factor that makes the Marauder look slower than it really is in comparative terms is the way the speeds were published in the Martin manuals. The manuals often list speeds at power settings well below maximum, usually around 1,500 horsepower per engine, which is maximum sustainable power, not the actual horsepower limit. I think it was reasonable of Martin to do it that way, but you have to keep this in mind when comparing the Marauder's published speeds to the absolute maximum speeds published for other airplanes in the same size range. Another factor that works against the Marauder in speed is the intended altitude range of the design. The Marauder does its best work around 10 to 14,000 feet. It doesn't have a supercharging system designed for high altitudes. Now, it was supposed to have one, but it never got it. We'll come back to that topic. A B-24 Liberator can exceed 300 miles per hour, but only at very high altitudes where drag is low for a given true airspeed. The Liberator can do this primarily because the plane's intercooled turbo supercharging system can generate a lot of horsepower even at high altitudes. I have a video that covers that if you're interested. The Marauder has a single-stage, two-speed, non-intercooled supercharger, no water injection. This is fine for low and medium altitude work, but it simply can't make a lot of power up high, and it's up high where you usually see the really fast maximum speeds of airplanes like the B-24, as well as most of the fighters. In fact, the gearing of the Marauder supercharger is set up in such a way that it doesn't even make a lot of power at medium altitudes. It's really a low altitude setup, and down at lower altitudes, the Marauders, at least in the early versions like the A models, were actually pretty fast for a bomber that size. Let's take a look at the manual. This is an early Marauder, as you can see from the manual's date of publication. Here is the cruise performance chart. I'll walk you through it. First of all, note that this variant of the Marauder is powered by R2800-5 engines. That's a pretty early version of the famous Pratt & Whitney R2800. Military power for this version is 1,850 horsepower, which is reached at 49 inches of manifold pressure and 2,600 RPM. However, the chart only provides speeds for power settings up to rated power, which is at or near 40 inches of manifold pressure and at only 2,400 RPM. For this variant of the R2800, that's only 1,500 horsepower, far short of the actual maximum. Still, this early version of the plane is pretty fast down here, especially at lower weights. Let's take a look. The lines for true airspeed are badly faded on the chart, so I'll darken in the lines at 280 and 310 miles per hour. I circled the markings for 290 and 300. As you can see, the B-26 can exceed 300 miles per hour from about 5,000 feet to about 21,000 feet. I shaded that in orange. It even nudges above 310 in a few places, even 320 in a very narrow altitude range. This is without maximum power, although it's also at only 24,000 pounds, which is pretty light for a B-26, even an early version. So this speed would be representative of a high cruise speed going home after dropping the bombs. As an example, at sea level, it can manage 281 miles per hour at 24,000 pounds and at rated power. Bump that weight up to 30,000 pounds and it slows down to 275, which was still fast compared to its peers. Here I've darkened the line for 320 miles per hour, and as you can see, the highest speed on this chart for the Marauder is about 321 miles per hour at about 13,500 feet. And again, that's at rated power, 24,000 pounds. There is a U.S. Army Air Force test of the plane from January of 1941 that shows very slightly faster numbers, 326 miles per hour at just over 14,000 feet. This test was at full throttle, but again, only at 2,400 RPM. So the supercharger wasn't giving full manifold pressure, only about 40 inches, once again, rated power. Sadly, there are no tests of the Marauder at actual full power, at least none that I could find. Still, 320 miles per hour isn't bad. We need to keep this in perspective. Not only does that make it one of the fastest low or medium altitude bombers in 1941, it was faster than quite a few fighters of the time, including a lot of Japanese and Soviet fighters. For what it's worth, I did the calculations for the plane at maximum power, and I come up with about 340 miles per hour for the plane's actual maximum speed. I talk about how to do that sort of calculation in my Key 84 series, and it's a pretty accurate method, just keep in mind it's by no means official. I graphed the early Marauder's maximum sustained speed here at 14,000 feet, where it can do 320 miles per hour. At that specific altitude, which is very near the optimal altitude for the Marauder, It's quite fast by 1941 standards. It's one of the fastest bombers in the sky, and certainly one of the fastest medium bombers, possibly the fastest. The numbers on this chart are pretty solid. The Marauder's numbers are straight from the pilot's manual and, as explained, are at rated power. The Ju-88 manual, if I'm reading it right, shows a maximum sustained speed of 242 miles per hour at 14,000 feet. I have to say that seems slow to me, slower than I thought it would be. Obviously, the Ju-88 manual is in German, so I'll put the chart at the end of the video and maybe some of our German speakers can translate it better than I can. I have seen a maximum speed of 270 miles per hour listed for the Ju-88 at 4,000 meters, which is about 14,000 feet, but I haven't been able to back that up with the manual. So I'll put both numbers here on the chart. Either way, the Marauder is the faster bomber, much faster. The Hurricane is only running 6.5 pounds of boost in this example. They were commonly running 12 pounds in 1941, but I can't find any tests of it that way. My best guess is that a Hurricane at 12 psi would be very slightly faster than a Marauder with both planes at 14,000 feet, maybe a couple miles per hour. Then again, we're comparing the Marauder's maximum sustained speed to the Hurricane speed with a short time limit. It would be very difficult in any sort of practical terms for a Hurricane to catch a Marauder. And there is an actual U.S. Army Air Force test of various fighters trying to catch various bombers. And it was found that in a level flight stern chase, it was, quote, impossible, unquote, for the Hurricane to catch the B-26. The Spitfire, P-40, and P-39 could catch the B-26 Marauder, but only after a very long stern chase, which of course would require operation far from base. Now back to our chart. The B-25 number is straight out of the manual, so no questions there. The I-16 number is for a late production best case I-16. I could not find numbers for it at 14,000 feet, but it will be slower up there than it is at 9,800, so the Marauder can outrun it with no real problem. It's much the same with the P-36. There is a lack of data, but the Marauder is faster any way you look at it. So the early Marauder, which is the one we're talking about so far, isn't slow. The slow reputation comes from a number of things. Comparisons at altitudes where it doesn't operate, comparisons to later or smaller aircraft, and comparisons against aircraft running at maximum power versus the Marauder at rated power. On the subject of rated power, in the Marauder it does not have a time limit, although it's not technically cruise power either, which is lower. The same manifold pressure value in RPM that is listed as rated power in the Marauder's manual is called maximum continuous for the R2800 engines in manuals from other aircraft manufacturers. You see, terminology was in a state of flux back then. So all things considered, the B-26, at least the early version, was pretty fast. Now, it should have been a lot faster, and would have been had it not been for some last-minute design changes, and I'll get to that later in the video. Next, I want to talk about another Marauder issue. It was dangerous, especially a dangerous airplane to train in. Keep in mind, we're still talking about the early models, and this is going to get complicated. Not only did the design of the Marauder A's have some real danger built in, the danger was compounded by rapidly advancing and misunderstood technology, pilot training that wasn't keeping up with the technology, and wartime production problems causing critical defects at the worst possible times in the plane's history. To put this into context, we really need to talk about the basics of multi-engine flying before we get into the Marauder's specific issues. It's important to have an understanding of these basics so you can fully understand the dangers and issues facing crews of twin-engine airplanes in World War II. I've been putting off talking about the multi-engine stuff on this channel for a while, which is why I haven't finished my P-38 or Mosquito videos, so we need to get this out of the way. Let's dive into it. Take a look at this picture from Aerodynamics for Naval Aviators. The point it's making here is that there is a speed below which the rudder will not have enough authority to counteract the yawing force from the operating engine if the other engine has failed. In this publication, that speed is called minimum directional control speed. There have been a lot of terminology changes through the years, but it's the principle here you need to understand. So far, it's pretty simple, right? In the event of an engine failure, the plane has to be going fast enough so that the rudder has enough authority to counteract the yaw from the operating engine. Otherwise, the pilot will have to reduce power to avoid losing directional control. That needed speed, according to the Navy here in this manual, is usually no more than 1.2 times the aircraft's stall speed with the aircraft in the lightest practical takeoff configuration. Of course, the Navy's diagram we saw involved jet aircraft. The same principle applies to propeller-driven aircraft, although with extra complications. Let's switch over to the Airplane Flying Handbook. What was called minimum directional control speed is now more commonly called VMC, so that's the term I'll be using. Think of it as velocity minimum control. Note that the exact definition has changed over the years, and confusingly, the correct definition isn't necessarily the current one. It's the one that was current at the time the airplane you are flying was certified. So watch out for that if you're taking a multi-engine check ride, because a tricky examiner can trip you up there. In this case, we're going to go with the older definition, of course, because we're talking about a B-26. Although I need to make it clear that this wasn't the definition during World War II. Back then, they didn't really have all this stuff worked out. In any case, VMC in practical terms can be thought of as the minimum speed at which the rudder has enough authority to overcome the yawing force from the operating engine when the critical engine suddenly fails. Now we need to define the term critical engine, so here you go. The critical engine is the engine whose failure would most adversely affect the performance and/or handling qualities of an aircraft. In a B-26, that's the left engine. It's important to understand why. The B-26 engines rotate clockwise as viewed from the rear. This picture depicts this situation pretty well. At positive angles of attack, the descending blades take the biggest bite of air due to something called P factor, which we talk about in another video. Now, this has the effect of moving the propeller's center of thrust to the right. So if the left engine fails, the center of thrust from the right engine will move to the right, thus increasing VMC because the operating engine essentially has more leverage to overcome the rudder. Now, if the right engine fails, the center of thrust on the left engine is closer to the fuselage. This gives the thrust less leverage over the rudder, thus reduces VMC. This is the reason that the left engine is the critical one on the B-26 or most other twin-engine planes with the propellers rotating the same way. Now, there are some airplanes, the early P-38s come to mind, which have a critical engine for another reason. The P-38s have counter-rotating props, so the thrust asymmetry is the same regardless of which engine quits. But early versions of the P-38 only have electrical generators on one engine, so the critical engine is the one which drives the generator, because the loss of that engine will limit performance because the batteries will run down in about 30 minutes, at which point it will be impossible to control the electric propellers. The B-26, as with most U.S. World War II twin-engine bombers, has an electrical generator on each engine. A loss of a single generator wasn't usually a big deal. However, a loss of both generators on the B-26 was a big deal. With only limited battery power to control the props and the other electrical systems, a turn back would usually be required. It wouldn't be able to complete its mission. Remember this later. It's going to come up later on in the video. Back to the minimum control speed, or VMC. The problem, or let's say the complication, is that there are a lot of factors that can affect it. It's not always the same speed in a given airplane. Thus, the manufacturers have to publish the speed in modern times with the plane in a specific and usually worst-case condition. So let's go through these factors to get an understanding of the variables that affect VMC. First of all, the operating engine should be at maximum available takeoff power. In the B-26A, that's 2,600 RPM, 49 inches of manifold pressure. And this should make sense to you, right? More power increases the yawing force into the dead engine. As we're looking for a worst-case scenario, because VMC is primarily a big deal in the event of an engine failure on takeoff, we reference the speed to takeoff power. Next, the propeller control should be in the recommended takeoff position. Okay, in the B-26A, that's going to be all the way forward because that's where it needs to be to get 2,600 RPM needed for takeoff power. That's where it's going to be on takeoff, plus it's a worst-case scenario because the propeller blade angle on the failed engine has a huge effect on drag, and that's going to be the high drag position. More drag on the dead engine side yaws the plane in that direction. The prop controls set for maximum RPM will give you maximum drag. Note that it specifies that the critical engine is windmilling. I'll come back to that later. There's also a note about auto feather, but the B-26 doesn't have that. That's something that came along later. Now, we have weights and center of gravity. In my opinion, these should be two separate things, so I'll tackle them that way. The center of gravity is the easier one to understand, so I'll start there. Airplanes pitch, roll, or yaw about 3 axes, all of which run through the center of gravity. That means it yaws about the center of gravity. The further back that point is, the less leverage the rudder has, and thus the more speed you need to be able to counteract the yawing forces from the operating engine. That should be pretty easy to understand. An aft CG increases VMC because it decreases the rudder's leverage. Weight is complicated. The official answer is that VMC increases as weight is reduced. That's the answer you give if someone asks you this question in an official capacity or during a job interview. Under certain conditions, it's absolutely true, and it's always true in a jet airplane. And it's true in a plane with counter-rotating props with the descending blades on the inboard side, and this is how many multi-engine training aircraft are set up. Thus, in many cases, it's true. Back when I did multi-engine training, and this was back in the 1980s, so a long time ago, I was taught the opposite, that VMC increases with weight. Here was the reasoning. Remember, they changed the definition. In the past, VMC was established with the loss of the critical engine, not a, quote, critical loss of thrust, unquote. We know what a critical engine is, but let's take a look at the official definition. And this is the current definition, and it's actually the only definition I've ever heard. Back to weight. Higher weights will require the plane to fly at a higher angle of attack with all other factors equal. Higher angles of attack will move the thrust lines further to the right. Thus, we have two situations to consider here, depending on which engine fails. One will increase VMC and one will reduce it. So I think that the statement that VMC goes up with a reduction in weight relates more to modern twin-engine aircraft with counter-rotating props and, of course, jet aircraft, because the extra weight resists the yaw when an engine suddenly fails. But in the case of an older prop-driven airplane, it's just not that simple. Weight going up could either increase or decrease VMC, depending on which engine you're talking about. Ideally, you want the plane's VMC speed to be as low as possible. For example, if it's below the stall speed of the plane, then it won't be much of a factor, as pilots are already trained to avoid stalls from day one. Pilots in multi-engine training already know how to avoid stalls, and they know how to perform stall recoveries. So if VMC is below the stall speed, they won't ever encounter it. However, VMC is usually well above the stall speed, especially in a World War II era bomber, the B-26 included. In fact, it's unusually high in the B-26. Remember, aerodynamics for naval aviators said that minimum control speed is usually 1.2 times the stall speed with the plane in its lightest takeoff configuration. Well, in the B-26, it's more like about 1.5 or maybe even 1.55 times higher. Not good, because that means there's a large speed range during the takeoff phase of flight, takeoff and initial climb out, where the plane could be flying but would be below VMC. Before we get back to the B-26, there is one more twin engine principle we need to know That's a speed called VYSE, which is the speed that gives the best rate of climb with one engine inoperative. Many lighter aircraft will have this speed marked on the airspeed indicator with a blue line. However, older airplanes don't have that marking, and heavier aircraft don't either. They use another method of denoting that speed. Note that VYSE only guarantees you the lowest sink rate. It does not necessarily guarantee that the plane will climb. Whether it can climb or not on one engine is another thing, and in regards to the B-26, it can if everything is going just right. The problem is that single-engine climb performance in a loaded B-26, or any bomber from the period, will be quite poor. Any twin-engine bomber, that is. Note that VYSE only guarantees you the lowest sink rate. It does not necessarily guarantee that the plane will climb. Whether it can climb or not on one engine is another thing, and in regards to the B-26A, it can climb on one engine if the plane is properly flown. The problem is that single-engine climb performance in a loaded B-26 or any medium bomber from the period will be quite poor. In fact, it's going to be poor in almost any twin-engine propeller airplane. You might think that because you lost one engine, you lost half your power, and that it should cut your climb rate in half. But it doesn't work that way. Yes, you lost half your power, but it's the power beyond what's needed for level flight that enables the plane to climb. I'll call this excess power. When you lose one engine, you often lose 90% or more of your excess power, plus you incur an additional drag penalty from the control displacement needed to keep the plane flying. This drops the climb rate of your heavily loaded bomber from something like 500 feet per minute to 50 feet per minute or worse. And believe me, when you're flying 135, 140 miles per hour and climbing at 50 feet per minute, it feels like you're not climbing at all. It's a pretty disturbing thing. Now, when you lose an engine up at altitude, this isn't too much of a problem. You may drift down to the plane's single-engine service ceiling, but unless you're over high mountainous terrain like the Rockies or the Alps, it's usually no big deal. Even if the plane won't hold altitude at all, the sink rate will usually be low enough that you're going to be able to reach an airport without any real difficulty. The big problem here is when you lose an engine on takeoff. This is the worst case scenario, and it's one that is very heavily trained in modern times, and it was in World War II to the extent that they could. Now, today, any check ride in a twin-engine airplane will involve an engine failure on takeoff, at least if the check ride is in the United States. However, modern jet airliners have so much thrust that even with the loss of an engine on takeoff, climb performance isn't usually a big problem. Of course, there are exceptions, certain airplanes, certain airports. However, in World War II, prop-driven bombers had a real serious loss of climb performance with an engine failure on takeoff, so this was a big deal. Let's go through a B-26 takeoff with an engine failure using the numbers and procedures from the manual so you understand what these guys were up against. The plane will be configured before takeoff with half flaps and the cowl flaps and oil shutters fully open. Very obviously the landing gear will be down. So the plane is in a high drag configuration, which will have a significantly negative impact on climb performance. In fact, if it's on one engine in this configuration with the dead engine's prop windmilling, a climb will be impossible, which is why cleaning up the drag after takeoff is so critical. So we start our takeoff. Initially, we maintain directional control with differential throttles, maybe a light touch of the brakes. In the B-26, as with most airplanes, especially U.S. airplanes, we can apply the brakes to one wheel at a time if needed to steer. Soon, the rudder will be effective, and that will provide enough directional control while rolling down the runway. Once the plane is clearly going straight, we bring the throttles up smoothly to max power, which again, 49 inches, 2,600 RPM. Now the next part of the takeoff procedure in the B-26 is going to come as a bit of a shock to most modern multi-engine pilots. The official procedure from the manual is to hold the yoke all the way back right after power is set and keep it there until the nose wheel comes off the ground. In other words, from the point power is set to the point when the nose wheel comes off the ground, the elevator is held in the full nose-up position in an effort to get the nose wheel off the ground as soon as possible. The nose wheel will come off the ground at about 60 miles per hour, at which point the pilot will manage the pitch until the airplane flies itself off the ground at about 105 miles per hour, maybe 110 at higher weights. Once the plane lifts off, the landing gear should be retracted right away in the B-26, and once any obstacles are cleared, the plane should be accelerated to about 150 miles per hour. Now, when the plane reaches 150 miles per hour, the crew can breathe a real sigh of relief. At that speed, even if an engine fails, it's not too big of a deal. The plane is already clear of obstacles. It's above both VMC and VYSE. So feather the prop, secure the engine, and start heading back to the airport. It's not a great situation to be in, but it's not that dire. The situation that is dire is when the engine fails at some point on the takeoff between 60 miles per hour and 140 miles per hour. When the nose wheel lifts off at 60 miles per hour until the plane lifts off at 110, an engine failure will render the plane unflyable. The pilot will have no choice but to close the throttle on the operating engine and try to stop the airplane. If he isn't quick, the plane is going to swerve off the runway because it's way below VMC and it's got one engine operating at takeoff power. Best case, he will be able to get the plane stopped straight ahead without hitting whatever was at the end. Of course, the outcome here depends a lot on the speed, weight, and runway length of the scenario, but in no case will the plane be getting airborne, and in some cases it's going to be a total loss. Now, once the plane is airborne, but before 135 miles per hour, it's much worse. At this point, the pilot will have to retard the throttle on the good engine and land. In cases where there isn't enough runway remaining, and that's going to be most of the cases, this will result in a crash. The problem here is that the B-26's VMC is 135 miles per hour. Keep in mind the term VMC didn't exist at the time. There isn't even a solid discussion of the concept in the B-26 manual. But there are all sorts of warnings not to let the speed drop below 135 on one engine, so I think that's a worst case VMC for the airplane. The procedures for takeoff in this plane leave a lot of time when the plane is in the air below VMC, and an engine failure in that range will bring the plane down. Keep in mind, no amount of pilot skill or training will rectify this. If the engine fails after takeoff, but before 135 miles per hour indicated, the plane is coming back down. Hopefully on a runway, but most of the time it's going to be resulting in a crash. Now, in a modern airliner like this one, this situation does not arise. Everything is planned out, so an engine failure at any time during takeoff will allow for either enough room to stop the plane on the runway or enough speed to continue the takeoff and climb away to safety. They will have a specific speed calculated called V1, which will account for aircraft weight, atmospheric, and other variables. Below V1, if the engine fails, they will abort the takeoff and have enough room to stop. At or above V1, they have enough speed to take off successfully. So why didn't the U.S. operate the B-26 this way? Why choose a method of takeoff that would put the plane at risk for such a long period of time on every single takeoff? Of course, that's not answered directly in any period documents, but we can take some pretty solid guesses. First of all, takeoff distance. As with most twin-engine World War II aircraft, it was thought that B-26s were going to be operating on forward and sometimes improvised runways, which would often be so short that the pilots would need to use whatever techniques would get them airborne in the shortest distance possible. At this point in history, paved runways were a luxury. When taking off from a soft grass field, it's normal to try and get the nose wheel up ASAP. In fact, that is the procedure you would normally use. I think that in many cases, they just didn't have enough runway to accelerate above VMC before lifting off, so they trained to get the plane off the ground as soon as possible. Also, there may have been tire speed limitations to be concerned with. I don't think so, but I haven't been able to find the tire speed limits for U.S. medium bombers. But there had to be one, and it's possible that 135 miles per hour indicated would overspeed them, especially at high-density altitude runways. I think the main reason was that they just didn't really have twin-engine tricycle gear procedures figured out yet. Previous twins were usually tail draggers, so an engine failure on the ground almost always meant aborting the takeoff. For those planes, it made more sense to get them off the ground as quickly as possible. Furthermore, few twin-engine airplanes could lose an engine on takeoff and climb. The DC-3 could if flown well, but it was one of the few. However, most of those earlier twins couldn't climb after an engine failure on takeoff, but had low enough stall speeds so that if you did have to ditch right after takeoff, it wasn't a death sentence. For example, an Avro Anson would come in at about 60 miles per hour, a loaded DC-3 at about 70 miles per hour. A B-26 ditching is going to hit the ground at a minimum of 105 miles per hour, probably closer to 120. That's a big difference for most of the older twins. Whatever the reason for the official takeoff procedures, the B-26s were in a very vulnerable position from the time the nose wheel got off the ground at 60 miles per hour until the plane was cleaned up and flying at about 150 miles per hour. That's a long time. And even if the engine fails between, say, 135 and 150, the pilot's got to feather the prop and get it cleaned up pretty quickly and not accidentally shut down the wrong engine. So there was a lot of pilot skill involved even in the better case scenarios. Of course, you might think that engine failures on takeoff would be very rare in the Marauder. After all, it's using the famous Pratt & Whitney R2800 engines, one of the best engines of the time, an engine known for its reliability. However, the R2800s initially were not super reliable. The Marauder was one of the first airplanes to use the then brand new R2800. New airplane, new design, new engine, and with the new Curtiss electric props. All of this stuff was being rushed into production in 1941 because even well before Pearl Harbor, it was felt that U.S. entry into the war was imminent. In fact, they were in such a rush that no prototype of the Martin Marauder was built. It went from the drawing board to production, as the plane had a lot of new technology in it, like a plastic nose, the powered upper turret, electric bomb releasing. It had a very interesting way of feeding ammunition to the tail gun, which enabled it to carry twice as much ammo as other U.S. bombers. There was a lot of technology in this thing, a lot of new technology, so you would probably expect a lot of issues that would need to be ironed out, and of course there were. The Marauder's Pratt & Whitney engines initially had injection carburetors with components made by a subcontractor. One of these components, a diaphragm, was made of a material that didn't hold up and would cause an engine failure, usually during takeoff or initial climb. There were other teething problems with the engine as well, but that was the big one. Now, most of these problems were solved pretty quickly, and the R2800s became amazing engines, and they became very reliable. But it was the B-26 and their crews that bore the brunt of the engine's initial teething problems, simply because the B-26 was one of the first, and depending on how you look at it, was really the first airplane to go into service with this engine. The electric props were another complication that contributed to the early accidents. The Curtiss electric prop was a pretty good piece of technology, but to work, as the name implies, they needed electricity. Some accidents were caused by crews running the batteries down, and then on takeoff, before the engine-driven generators would start doing their thing, the prop controls would fail because of low voltage. If a prop overspeeds on takeoff, it can result in a sudden engine failure, which, as we discussed, if that happens when the plane is below VMC, it is most likely going to end in a crash. Now, this was quickly rectified, the propeller problem, through the use of a battery cart, which is literally just like a giant sort of low-slung shopping cart full of batteries. And they would plug this battery cart into the plane during pre-flight and engine start, and later on the planes would have an auxiliary power unit in them. So this whole situation was really something that wasn't caused by the electric props or the plane itself, but rather the pilot and ground crew's lack of familiarity with the new technology. In most previous twin-engine airplanes, you could blast off without even thinking about the electrical system and the plane would perform just fine. But that wasn't the case with this new generation of complex twins. It's hard to understand just how fast the technology was advancing in the mid to late 1930s. Consider that many B-26 squadrons upgraded to the plane from the Martin B-10, seen here over Hawaii in 1941. It doesn't even have constant speed props, the B-10 that is, let alone Curtiss Electrics. The B-26 was a huge leap forward from the B-10. The Marauder is far faster, more than twice the weight with twice the horsepower, has much more complicated systems. The B-10 has half, actually less than half the wing loading and much lower takeoff and landing speeds. The B-26 was such a leap forward that even Martin's own test pilot for the plane had never flown anything with tricycle landing gear until very shortly before his first flight in the Marauder. Ironically, they got him experience in a tricycle gear aircraft by getting North American to let him fly a B-25 prior to his first flight in the B-26. In short, we had a situation with rapidly advancing technology and performance which outpaced pilot training and doctrine for multi-engine flying. Combine that with a rush into wartime production and the resulting and somewhat normal for the time initial problems that cropped up, and we end up with a very high accident rate for the early B-26s. B-26s had 165 accidents per 100,000 hours. That statistic comes from this book. They don't list a source for it, but the number does make sense, so I think it's correct. Now, that's a lot of accidents. To put that into perspective, if modern airliners in the United States had that same accident rate, we would see about 75 airliners crash per day just within the United States. I think that should drive home how high the accident rate was for the B-26. Now, the B-26's accident record was terrible, but the same was true for most World War II airplanes. This wasn't at all unique to the B-26. For comparison, the B-25 Mitchell, which was considered a pretty tame airplane, had about 105 accidents per 100,000 hours, so it was quite a bit better, but still really bad. And the Douglas A-20 Havoc and Lockheed's P-38 Lightning were about on par with the Marauder. So while Martin's airplane did have a lot of accidents, it wasn't far worse than its contemporaries. However, it was the plane that suffered the greatest hit to its reputation, partially because of where its introduction fell on the timeline and because it got quite a bit of extra scrutiny from the Truman Commission. The Truman Commission, and rightly so, looked into war production waste. They looked at the B-26 and they saw a plane that didn't have the speed initially promised. It had a poor safety record and it was very expensive. Let's talk a bit about the speed. I know I covered that before, but there's more to discuss. As initially designed, the Marauder was intended to have a top speed of around 400 miles per hour, and it would have had the realities of the impending U.S. entry into the war not rushed the plane into production. According to the plane's designer, Peyton Magruder, seen here with Jimmy Doolittle, the plane was originally intended to use the Wright 3350 with turbo supercharging. By the way, I want to mention that Glenn L. Martin was not an engineer. He was, however, an accomplished pilot and a very good businessman. He seemed to excel at finding good engineers to work for him. In fact, Donald Douglas was a Martin engineer at one time, who, of course, went on to create Douglas aircraft. Back to Magruder. In a letter to Bernard Mallon, an author who wrote a book about the B-26, Magruder discussed several proposed power plants. The Wright 3350 with turbo supercharging, which would have given it a top speed of 414 miles per hour. However, the engine wasn't ready in time. It first ran in 1937, but development of that engine took a while, and by the time it was ready, the B-26s were already established with the R-2800s, and the B-29 Superfortresses were hogging most of the 3350 production anyway. Another proposal, and the one that Magruder seemed to want, was the R-2800 with turbo supercharging, giving it a top speed of 392 miles per hour. This was the setup the B-26A was designed around, but the plane was ready way before the turbos. Now, there were turbochargers out there at the time. They were on the B-17 and on the B-24s pretty soon, but they were way too small for the R-2800. Remember, the B-17 used 4 much smaller engines. The bigger turbo needed for the R-2800s, as used on the P-47 Thunderbolt, for example, just were not ready in time for the B-26, and they couldn't delay the plane due to what they thought, and what happened to be, the impending U.S. entry into World War II. They also looked at a 2-stage, multi-speed, mechanically driven setup, much like what was in the Corsair, but again, time just wasn't on their side. According to Magruder, this would have given the plane a top speed of 368 miles per hour. As we know, the Marauder ultimately settled on a single-stage, 2-speed supercharger in the interest of time, but the entire airframe had been designed around that 400 mile per hour top speed, the wings, the fuselage, and everything. Without the turbo supercharged power plants, ideally Martin really should have designed a new wing optimized for the lower speeds. Plus, the weight of the plane kept going up, which didn't help things. But they just didn't have the time to do that. So to a layperson, it looked like the B-26 didn't ever reach its design goal, which it didn't, and that's how it looked to the Truman Commission. But this was really a result of wartime production pressures, not a flaw in the plane's basic design and not a failing of Martin aircraft. As for the safety issues, those were valid complaints, although the B-26 probably took more criticism for this relative to its contemporaries than was really justified. The result was that Martin did increase the wing span, same wing design, they just made it longer, and they changed the vertical stabilizer and rudder, and those things did help. The later B-26s were about equal in accident rates to other comparable planes of the war, but they were also a little bit slower than the early B-26s. Now, as for the expense, yes, the B-26 was very expensive, far more so than a B-25 Mitchell. The cost of a Marauder is actually pretty close to that of a B-17 Flying Fortress. The Marauder has 2 expensive engines, remember there are 2800s, a complex structure, a Norden bomb sight in many cases, a torpedo director. It was the first plane to have Curtiss Electric 4-bladed propellers. All this stuff adds up. Take a look at the fuselage. Every single panel not only has compound curvature, but its own unique compound curvature. It just wasn't designed to be an inexpensive airplane to build. The cost was a valid criticism, but I don't think it was a case of war profiteering. It was just a costly airplane to build by design, partially because it was designed to be a 400 mile per hour airplane, and partially because it used a lot of new at the time technology, and new technology is always expensive, and this plane was packed with it. Martin responded to all of this criticism, and they took an interesting path, one which seems to have worked out pretty well for them, so I think they were pretty smart. Rather than explain the reasons it wasn't as fast as promised or why it cost so much, they stood on the plane's combat record. Glenn Martin was no dummy, and he knew how to play the game within what we would now call the military-industrial complex. That term didn't exist at the time. He ran a lot of magazine ads in aviation publications like this one, and for a time was the chairman of the National Aircraft War Production Council, the records of which now, interestingly enough, are in the Truman Library. To shore up the reputation of the Glenn L. Martin Company, an article was commissioned to appear in Popular Mechanics. It's actually a pretty good article. It does exaggerate the B-26's contributions at the Battle of Midway, but otherwise the article is quite accurate. I think the entire reason for putting this in a magazine, in this magazine rather than an aviation-specific magazine, was in an effort to sway public opinion. The entire magazine is an interesting read. It's interesting to look through these old magazines and realize that in some ways, the more things change, the more they stay the same. I should mention that I have this magazine in the Patreon section in its entirety, as well as this one and, of course, the pilot manuals for the airplane. Back to the B-26. It did have a good combat record. One of its claims to fame is the plane's very low loss rate once in combat. While a lot of them were lost during training, once they made it into combat, they had a pretty good chance of survival relative to other bombers. Statistically, the B-26 had a lower loss rate in combat than any other U.S. bomber, and I believe any other World War II medium or heavy bomber. Statistics on this stuff are a little bit murky when you get into air forces of countries other than the U.S. because they kept track of things in different ways. Now, at least some of this, the Marauder's low loss rate, is due to the way the plane was used. Generally speaking, the B-26s in Europe operated in areas where Allies had some fighter presence, usually a pretty strong fighter presence. As compared with the U.S. four-engine bombers, B-26s were rarely flying in large numbers, unescorted, deep into enemy territory, in situations where they would run into enemy fighters. They never had to face the Luftwaffe fighters to the extent that the four-engine heavies did. Now, that's not to say that Luftwaffe fighters didn't shoot down B-26s. They did, just not in tremendous numbers by World War II standards. Furthermore, the B-26s were rugged and with a lot of defensive firepower, so it was risky for the enemy fighters to attack them. The Luftwaffe fighters most suited for taking them down were the twin-engine heavy fighters. However, these were pushed back as soon as P-47 started flying over Europe. As you can see here, by March of 1944, almost all of the German twin-engine daytime fighters had been pushed way back from the coast. These planes simply could not face U.S. Army Air Force fighters without disastrous losses. So the Germans kept moving them back more and more as the U.S. fighters kept going deeper and deeper into Axis territory. Here is what the picture looked like about a month after D-Day. Thus, the B-26s rarely had to face the planes that should have been their deadliest opponents. Furthermore, when B-26s did go deep into German territory without escorts, and they did do that, the German fighters often ignored them. Let me explain. The U.S. Army Air Force thought that by sending B-26s to raid German airfields, it would either result in the destruction of German fighters on the ground or force the Germans to attack the Marauders and thus leave the four-engine heavies alone. This didn't work. The Germans usually had already moved the fighters by the time the Marauders arrived on the scene, and I don't think there was even one single time when the German fighters went after the Marauders when they knew of B-17s or B-24s that were inbound to bomb a city. The result was that the Marauders' survival rate went up partially because the German fighters were simply going after bigger game. Of course, this isn't the entire reason for the low loss rates. The B-26s did fly a lot of dangerous missions, and the plane's redundant systems and overall ruggedness did help get it home. I don't want to cover the entire operational history of the B-26. This isn't that kind of channel, and it would take me a really long time, but here's the gist of it. In the Pacific, they did fly as torpedo bombers at Midway. There were only 4 of them, not nearly enough. They didn't hit anything with their torpedoes, or if they did, the torpedoes didn't explode. U.S. torpedoes were having some real problems in 1941, 1942. The Japanese Zero fighters defending the fleet flew head-on attacks against the B-26s. That was a pretty good idea. They shot down 2 B-26s, and the B-26s shot down 1 Zero and strafed a Japanese carrier, causing some casualties. The 2 remaining B-26s did make it back to base, but were damaged beyond repair. This is generally thought of as a poor showing for the plane, but we have to consider that sending only 4 airplanes against the Japanese fleet, comprised of 4 carriers and a lot of other warships with anti-aircraft guns, at a time when the Japanese pilots were at their very best, that just wasn't a solid plan to begin with. The U.S. Army Air Force crews flying the B-26s had pretty minimal training at that point with torpedo bombing, and the B-26 is a tough airplane to use for torpedo bombing anyway because it's so fast. I think the fact that the 2 planes made it back is a testament to the Marauder's speed and durability. Up in the Aleutians, the B-26s did sink the Japanese destroyer Oboro, but did not have any successful torpedo attacks. Strangely, one B-26 did drop a torpedo onto the flight deck of a Japanese carrier, but it didn't explode. It simply rolled off into the sea. I don't know the full story there about why it dropped a torpedo onto the flight deck, but that's what happened. The U.S. Army Air Force didn't have much experience attacking ships at this point, and the B-26 was a tough plane to learn with. That said, the Royal Air Force did have some success attacking ships with the B-26 and did have successful torpedo attacks with the airplane, so it could do it. But the U.S. Army Air Force decided pretty early on to go with the B-25 Mitchell in the Pacific Theater and use the B-26s over on the other side of the world. The Marauders flew with the U.S. Army Air Force in the Mediterranean theater, and when used at low altitudes or when running into enemy fighters, losses would be pretty high. However, at medium altitudes and when escorted, losses were very low, so that's how they started to operate them. Over Europe, the U.S. 8th and later the 9th Air Forces operated the Marauders with great success and relatively low losses. Of course, there were some missions that didn't turn out too well. For example, in 1943, they raided a power station on the Dutch coast, which had already been hit twice by the British. The B-26s failed to destroy the target and were sent back only 3 days later. Very risky. They were really pushing their luck going back to the same target so soon, and as a result of the previous raid, only 11 planes were available for the mission because, of course, some were damaged. They might have pulled it off, but one of the planes suffered a double generator failure. What are the odds? And that plane had to turn back. The pilots of that plane climbed to 1,000 feet for the return trip to England, which was the procedure for a turn back at the time. However, this put the plane up high enough so it could be seen on German radar and most likely gave warning to the Luftwaffe that something was up. All 10 of the remaining Marauders were shot down without hitting the target. This type of fiasco was the exception and not the rule. Overall, B-26 losses were low and bombing accuracy was high. In fact, numerous sources, including British sources, say it was the most accurate medium bomber of the war. I think the high point of the Marauder's service was on D-Day. On that day, according to the Smithsonian, the B-26s were the only bombers to hit their targets. I think it's more accurate to say they were the only bombers to hit their targets in large numbers and with meaningful effect. The U.S. 4-engine heavies generally missed the beaches with their bombs falling well inland. However, a few stray bombs did hit the beaches, and the heavy bombers did create problems for the Germans behind the lines, but in no way did they do what they were supposed to do, which was take out the German defenses on the beach. In any case, no excuses have to be made for the B-26s on that day. They hit Utah Beach hard, and for the most part, they came in low below the clouds. They knocked out German defenses, they tore up the obstacles that were on the beach intended to impede tanks and other things, and they created foxholes for the troops. This had a huge effect on the invasion. Casualties at Utah Beach were incredibly low, only 197 men, and this was in no small part to the B-26s. For comparison, 2,500 men were lost on that same day at Omaha Beach, where the 4-engine heavies were supposed to pound the German defenses. The U.S. 4th Division on Utah Beach actually lost fewer men on D-Day than they lost practicing for the invasion back in England. I think that really puts into perspective just how low the losses were at Utah Beach, and the B-26s were a big part of that. The U.S. and British aviation efforts on D-Day were massive, but are not discussed much because they were not as successful as hoped. Plus, they resulted in a lot of collateral damage to the French. This has sort of worked against the B-26 because its success on D-Day tends to get overlooked, and if discussed, it raises an awkward question that people at the time didn't want to talk about. If the B-26s succeeded, why didn't the heavy bombers? Well, the easiest way to deal with that question is just avoid it. Don't mention the B-26 on D-Day, which is what we see in the Hap-Arnold diaries and in the official history of the 8th Air Force. They just don't talk about it. And thus the B-26 never really got its time in the sun like the B-25 did for the Doolittle raid. I have to consider the B-26 to be a pretty good airplane. The criticisms against it are generally pretty weak. Speed, expense, and safety. We already talked about speed and expense. I have a few more things to say about safety. Was the B-26 too unsafe? It's tough to answer that question, especially because we have to consider it in the context of World War II aviation. I mean, by modern standards, yes, absolutely. The thing is a borderline death trap by modern terms. But when you're looking at World War II stuff, it's completely different metrics you have to consider. This might turn into a discussion that is as much philosophical as it is about aviation specifically. But consider that all of us could improve our safety at some cost. You could drive a safer car or ensure all the walkways around your home have anti-slip compounds. You could put those anti-slip compounds everywhere in your home. For that matter, maybe you shouldn't even leave your home. You could pay someone else to run all of your errands. Getting into an airplane, especially back in the 1940s, created some exposure to danger. The safest thing we can do with an airplane is lock it into a hangar, put guards around it, and never let anyone go anywhere near it. But obviously, if we intend to use the airplane for its intended purpose, we're going to have to accept some level of risk. Well, with a warplane like a World War II medium bomber, this is even more complicated because some of the very things that would make the plane safer in training or in day-to-day flying might also make it less safe, less likely to survive in combat. For example, the B-26 could have been made safer in many situations by lowering the wing loading via less weight or more wing. If they could have lowered VMC, VYSE, and the stall speeds by a significant margin, the plane would have been safer in the engine failure on takeoff scenario we discussed. However, it would have also been slower, which would have increased the exposure to enemy action to the crews in the plane when on combat missions over enemy territory. Designers of military combat aircraft usually sacrifice some level of safety in normal operations for performance in combat to improve the plane's chances in battle. For example, here's an F-14 Tomcat. It has a maximum weight of just over 74,000 pounds. Here's a Douglas DC-4. It weighs about the same, actually a little bit less. Notice that the DC-4 has dual main wheels. If one blows out on takeoff or landing, the pilots will have a relatively easy time dealing with it because the other tire will take up the load. It would be very hard to find a civil or transport type aircraft in the 60,000 pound range or heavier that doesn't have dual main wheels. In fact, modern airplanes usually start to have them down in the 12,000 pound range. However, nearly every military fighter has a single main wheel. I can't think of any that don't. They are making a sacrifice in the interest of aircraft performance. Less weight in tires and wheels helps performance, but at a greater risk in the event of a blown tire. Then to partially reduce that risk in the event of a blowout, they usually have some sort of procedure. They either change the tires more often or inspect them more often, they use better tires or whatever. The point is that sacrifices in safety are being made for performance and combat capability, and it was the same in World War II, and it was the same with World War II bombers. If you make it a safer airplane in day-to-day operations, it may become less effective as a combat airplane. How many additional combat losses should a manufacturer accept in the interest of decreasing the non-combat losses? I don't know the answer to that, but I'm pretty sure it's not a 1-to-1 ratio because in combat, there are extra lives on the line, which are very difficult to quantify. For example, if the B-26s had failed at Utah Beach, what would the resulting loss of life been? I don't know. The balance of safety versus mission capability is a very complex matter. Sure, the F-14 Tomcat wasn't exactly a safe airplane, but its mission capability in terms of fleet defense was so good that it was probably worth it. Back to the B-26. Yes, it was dangerous in training, but its combat record, in my estimation, more than makes up for it. I do think they could have operated it more safely. The methods used for takeoff were dangerous, no question about it. But if taking off from a grass field or a short field, the method they used was really the only way to do it. Early in the war, we didn't know that the plane would eventually be taking off from long runways in England. Nobody really knew what to expect, so the methods used for takeoff were the methods that made sense to prepare for what they thought would be typical military fields. Martin did go with longer wings and a larger rudder, which helped, but it really needed another wing entirely. That wing was intended for a 400 mile per hour airplane, but with the pressures of wartime production, changing to an entirely different wing design just wasn't in the cards. So they went with a longer version of the same wing, and that makes sense. Of course, another way to look at this was that the plane's wing was just fine. What it really needed were different engines, so it would have the speed to match its wing. When you start to look at that option, it becomes clear that it wouldn't have worked out well. The Wright R-33 engines had a lot of problems, and those problems weren't worked out until pretty late in the war. The turbo-supercharged R-2800s would have been a good choice in terms of performance, but using 20/20 hindsight, I don't really see a lot of cases in which the B-26s would have been used for high-altitude operations when there were plenty of B-17s and B-24s to go around. The B-26 worked out just fine as a medium bomber, and for that purpose, its more simple single-stage dual speed supercharged engines were just fine. In the end, I think that despite its faults, the B-26 was the right airplane for the U.S. Army Air Force, and it was there when it was needed in 1941, and crews were trained in it ready to go right at the point the U.S. entered the war. If I had to fly a U.S. bomber into combat over Europe during 1943 or 1944, I would choose the Martin B-26. Even in 1945, it would be my second choice, only behind the much more advanced and more capable Douglas A-26 Invader. The Martin B-26 Marauder was a true war-winning airplane, and it's one that got the cruise home.